3i Atlas should never have been in this place. It was supposed to slow down. Every calculation said it would. Every model, from NASA's JPL to the European Space Agency's orbital labs, predicted that as the interstellar object 3i Atlas approached perihelion, the immense gravity and radiation of the Sun would finally begin to tame its speed. But that isn't what happened. In the hours surrounding its closest pass to the Sun, 3i Atlas did something that no natural body should ever be capable of. It revealed a new, measurable anomaly, not a flare, not a fragmentation, but a change in motion. Subtle, precise, and mathematically impossible. The readings came in one by one, from observatories in Hawaii, Chile, and the Canary Islands. Each dataset showed the same curve. Instead of decelerating as the models demanded, 3i Atlas appeared to accelerate, ever so slightly, but unmistakably. The signal was clean. The acceleration was real. At first, no one believed it. Instruments were recalibrated, timestamps rechecked, reference stars verified. The results held. The orbit didn't bend the way it should have under gravity alone. It shifted, as if something inside the object had responded to the Sun's proximity, adjusting, correcting, compensating. This wasn't noise. This wasn't an illusion. This was motion with purpose. And so, tonight, we're tracing that signal, step by step, through the telemetry, the spectral silence, and the pulse hidden in the light. We'll explore what it means for an object born beyond the solar system to act as if it understands the star it passes. Because if the numbers are real, if this pattern holds, then 3i Atlas may have just rewritten what we know about interstellar matter. Across multiple observatories, the object's brightness, polarization, and reflectivity all changed in perfect sync with the acceleration event. It didn't just react to sunlight, it seemed to use it. The ratios between energy input and velocity were too exact to be random, almost as though 3i Atlas was obeying a law we haven't yet written down, or following instructions we didn't know existed. That's the mystery we're stepping into tonight. Because for the first time since it entered our solar system, 3i Atlas has crossed the line between the predictable and the deliberate. It has shown behaviour, not chaos, not chance, but pattern. And if that pattern continues, the implications reach far beyond astronomy. Before we begin, make sure to like this video and subscribe so you don't miss what comes next as the data unfolds, frame by frame, night after night. Tell us where you're watching from, and the time right now where you are. Because as of tonight, the story of 3i Atlas has changed again, and somewhere, millions of kilometers from Earth, that story may still be unfolding, silently, precisely, under the light of the same sun that powers every movement we're about to uncover. This is the 3i Atlas channel, calm, focused, and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to enter the giveaway for our exclusive 3i Atlas hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. It began quietly. No visible eruption, no dramatic burst of light. Just a point of data on a trajectory line, and a silence that carried more weight than any explosion could. On October 29, 2025, the interstellar object known as 3i Atlas reached its perihelion, the closest point to the Sun in its hyperbolic journey through our solar system. To most astronomers, this was supposed to be a routine milestone, a predictable dip in orbit, governed by nothing more than the equations of gravity and the laws of thermodynamics. But what happened at that precise moment changed everything we thought we understood about this visitor. Perihelion is more than a position in space. It's a crucible, a test of survival. At 136 astronomical units from the Sun, the radiation pressure, solar wind, and tidal stress reach their peak. Natural comets tend to flare here. Their icy surfaces sublimate, spewing vapour and dust that form brilliant tails and subtle thrust forces. Most lose mass, some fragment completely. But 3i Atlas didn't behave like any known comet. Instead of showing expected thermal and visual signatures of violent outgassing, it remained eerily stable. Bright, yes, but without the chaotic flicker that comes from escaping gas. And then came the data point that didn't fit. Within hours of perihelion, the heliophysics instruments aboard NASA's Punch and ESA's solar orbiter began recording a faint but measurable deviation. The motion of 3I Atlas, when extrapolated against the Sun's gravity and planetary perturbations, showed an unexplained acceleration. It wasn't large, roughly a few millimeters per second squared, but it was persistent and precisely timed. In physics, consistency is often more meaningful than magnitude. This wasn't random turbulence or solar radiation jitter. It was a pulse. Smooth, directional, deliberate. Inside observatories around the world, researchers began rechecking their data. Parallax readings, Doppler shifts, frame stacking, everything pointed to the same result. The object had gained speed when it should have been losing it. The Sun's gravity should have pulled it inward, slowing it slightly as it climbed out of Perihelion's well. Instead, 3I Atlas accelerated outward. To anyone studying orbital dynamics, that's a contradiction of the first order. Gravity doesn't give back what it takes, unless something else intervenes. For the scientists following the event in real time, the feeling was a mix of awe and disbelief. These were the kinds of anomalies that once surrounded Oumuamua in 2017, the first interstellar visitor that also displayed a small, unexplained push away from the Sun. Back then, the data was too limited, the observations too brief, but with 3I Atlas, the measurements were continuous, triangulated from multiple instruments. This time, the evidence was cleaner, the margins of error smaller. And yet no one wanted to say the obvious word, propulsion, because propulsion implies purpose, and purpose implies something more than nature. So the official statements remained cautious. Non-gravitational acceleration detected, read one internal memo from the Jet Propulsion Laboratory. Further analysis required. As the object rounded its closest approach, another curiosity appeared. A transient blue shift in its reflected light. A colour change that hinted at surface alteration or structural reorientation. In natural comets, colour variations are gradual, caused by evolving dust composition. In engineered materials, they can appear instantly when surfaces rotate or unfold. The timing, just minutes after perihelion, was impossible to ignore. From that moment, 3I Atlas was no longer just a curiosity. It became a case study, a living experiment in the limits of celestial mechanics. Was the acceleration caused by hidden jets beneath a crust of mixed ices? Was it the pressure of sunlight on a reflective surface larger than anyone expected? Or was it something entirely new, an object responding actively to solar energy in ways we've never seen before? As the first data packets left the deep space network that night, one conclusion was already clear. The perihelion of 3I Atlas wasn't just another waypoint on its hyperbolic path. It was an event, the precise moment when an interstellar object behaved as though it understood the Sun not as an obstacle, but as an opportunity. The story of 3I Atlas had officially changed course. The first numbers came in at 0214 UTC. They looked ordinary: positional coordinates, time-stamped telemetry, and light curve data. Nothing unusual at first glance. But when analysts compared the new readings against the pre-perihelion models, a quiet alarm rippled through NASA's deep space network. The fit didn't hold. The object's predicted position was off, not by kilometers, but by thousands of kilometers, an offset far beyond what measurement noise or solar wind pressure could explain. Every orbit model had agreed on one thing: by the time 3I Atlas rounded the Sun, it should begin to decelerate. Gravity's pull would still dominate, dragging the object ever so slightly inward as it left perihelion's curve. Yet the tracking data showed the opposite trend. The radial component of its velocity was increasing. Instead of slowing, it was speeding up. The instruments that caught it weren't even designed to detect interstellar anomalies. The Wide-Field Imager 3 aboard NASA's Punch satellite had been monitoring solar outflows, not distant objects. But because 3I Atlas crossed its field of view during perihelion, engineers later realized they had captured a high-fidelity time sequence, frame after frame showing an object accelerating away from the Sun. The derived figure was astonishing, roughly 135 kilometers per day squared of outward acceleration. For comparison, a typical comet's outgassing would generate a force about 10 times smaller, and even then, it would leave unmistakable visual traces, jets, plumes, or at least spectral emission lines. 3I Atlas showed none of that. At first, mission controllers suspected an error in the imaging pipeline. Cosmic ray strikes can skew centroid readings, and sunlight scattered off the instrument housing sometimes produces apparent motion where none exists. But after independent calibration, the shift remained. 2 other datasets confirmed it: optical astrometry from the Cerro Tololo Observatory in Chile and magnetometer data from ESA's solar orbiter. All 3 sources recorded subtle but synchronous perturbations in trajectory, matching within 0.2 sigma, a level of agreement too tight for coincidence. In the following 48 hours, the data review teams met in late-night calls that stretched past dawn. Every variable was rechecked: exposure timing, parallax baselines, atmospheric distortion, even the catalogue of background stars used for reference. One by one, the possible explanations fell away. The conclusion was uncomfortable, but unavoidable. Something had imparted additional momentum to an object that should have been passive. The word propulsion started appearing in the internal chat logs, usually followed by question marks. The Jet Propulsion Laboratories Navigation Division drafted a summary labelled Non-Gravitational Component under investigation. To avoid public confusion, NASA's spokesperson simplified the language for release. Unexpected acceleration detected cause pending analysis. But within the scientific channels, the tone was far less neutral. The question wasn't if the anomaly was real, it was how. Data scientists plotted the brightness curve against the acceleration data and found another coincidence. The 2 peaks overlapped. As luminosity increased, so did outward thrust. Yet spectroscopy offered no evidence of dust or gas. It was as if the object became more reflective precisely when it began to accelerate, suggesting a link between light and motion, the exact signature you'd expect from radiation pressure interaction on a large mirror-like surface. Meanwhile, Avi Loeb's research group at Harvard modelled the event using light-sail physics. Their simulations showed that an ultra-thin reflective sheet, only millimetres thick but hundreds of metres wide, could produce the same delta V under the observed solar flux. It was speculative, but the math worked. And for the first time since 3i Atlas entered our system, the word artifact appeared in a peer-reviewed draft. Still, the skeptics held ground. Some argued that subsurface carbon monoxide vents could trigger brief thrust pulses invisible in the visible spectrum. Others pointed to microfragmentation, the release of fine dust grains that alter photometric readings without changing mass significantly. But none of those models reproduced the smoothness of the recorded acceleration curve. Nature's forces act in fits and bursts. This one looked engineered. By November 1st, after days of around-the-clock analysis, the official telemetry summary reached the International Astronomical Union. It contained just one understated sentence. A sustained non-gravitational acceleration component was observed between October 29th at 7 and October 30th 4 UTC. That sterile line concealed a profound realization that somewhere between Mars and the Sun, an object from another star system had moved in a way that no rock, ice ball, or comet ever should. The data, stripped of emotion, told a story bigger than any headline could capture. The universe had just whispered a quiet, mathematical yes, and no one yet knew what question it was answering. By the morning of October 31st, the anomaly could no longer be treated as a sensor glitch. Multiple observatories, separated by continents, oceans, and even political boundaries, had now detected the same deviation. What began as a curious data point inside NASA's telemetry stream was turning into a global investigation. The question was no longer if 3i Atlas had accelerated, but how certain we were that the numbers were real. At the European Southern Observatory in Chile, the sky was clear and dry. Their 3.6-metre telescope had been programmed to reacquire 3i Atlas the moment it re-emerged from solar conjunction. The data came through at dawn, faint but clean, a dot shifting ever so slightly faster than the orbital models predicted. Using differential astrometry, comparing the comet's position to reference stars in the same frame, the team calculated a positional drift of nearly 4,800 kilometres over a 20-hour window. It was small, but consistent with NASA's own readings. Hours later, the Canary Islands telescopes confirmed the same offset. The timing of the anomaly matched to within 6 minutes. Both hemispheres, both datasets, identical trend. To the untrained eye, it looked like nothing more than a tiny step on a long curve. But to the scientist tracking an object that should obey Newton's laws to the millimetre, it was extraordinary. Cross-verification is the gold standard of astronomy. Every instrument has its biases, atmospheric distortion, pixel noise, mechanical flexure. Only when independent systems see the same signal can an anomaly be trusted. So, a task force quietly formed under the International Asteroid Warning Network. They called it the 3I Atlas Post-Perihelion Working Group. Its members came from NASA's Jet Propulsion Laboratory, the European Space Agency, Japan's Subaru Observatory, and several university observatories across the Southern Hemisphere. Their goal was simple: eliminate every natural or instrumental explanation. Data started flowing into shared repositories, each observation time-stamped and corrected for local weather, temperature, and instrument drift. When analysts overlaid the plots, a perfect alignment appeared, a smooth, shallow arc, diverging from the predicted path by exactly the same gradient in every dataset. If it had been an error, it would have scattered randomly. Instead, it drew a single coherent line across the charts. Even radio observatories joined the effort. The Very Long Baseline Array in North America, using antennas spread over thousands of kilometers, attempted to triangulate the object's motion through parallax. They measured micro-arc-second shifts in position that confirmed the optical data within 1.2%. That's the kind of precision used to track spacecraft, not comets. By now, every major space agency was quietly paying attention. The Minor Planet Center updated 3I Atlas's orbital parameters, labeling it with an asterisk, a notation reserved for trajectories under active revision. And yet, while the numbers matched, the interpretation fractured. European teams leaned toward a photometric artifact. NASA insisted the residuals were physical. Japanese and South Korean observatories, reviewing their own images, sided with NASA. "The deviation is real," one Kyoto astronomer wrote. "It's measurable, directional, and synchronized with perihelion. We see no noise explanation." Then came the control test. A separate asteroid, 20 VU3, passed through the same sky region days later. Every telescope repeated identical observation procedures. The asteroid's orbit fit predictions perfectly. No deviation, no unexplained drift. The instruments were working flawlessly. By early November, a report circulated privately among the participating observatories. Its language was restrained but unmistakable. Independent Earth-based observations confirm the existence of a non-gravitational acceleration in the trajectory of C2025 N1, 3I Atlas, consistent across multiple platforms and wavelengths. 16 telescopes, 5 continents, 3 orbital vantage points, all converging on the same conclusion. For the public, this development barely made headlines. But inside the global astronomical community, it was seismic. The cross-verification from Earth meant that whatever force had acted on 3I Atlas was not an illusion, not a software quirk, not an observational coincidence. It was physics, unexplained, persistent, and now beyond dispute. And somewhere between the lines of those clinical data tables, a deeper realization began to grow. That our planet, scattered with telescopes and radio dishes, had just watched something in interstellar space move on its own. It lasted just 12 minutes. A burst of light so brief, so contained, that most sky surveys never even registered it. But the few instruments pointed in the right direction that night captured something extraordinary. A flash at perihelion, originating precisely from the coordinates of 3I Atlas. Not a flare, not a dust plume, and not the familiar radiance of sublimating ice. It was cleaner, sharper, and unlike anything natural observers had seen before. The alert first came from the Solar and Heliospheric Observatory, SOHO, whose ultraviolet cameras were scanning the inner heliosphere for coronal events. At 22:31 UTC, a transient bright spot appeared in the imaging data, small, localized, and spectrally distinct from solar noise. The point source flared in the 400 to 700 nanometer range, roughly the same wavelengths as visible sunlight, but with an unusual polarization signature. It wasn't scattered, it was reflected. Simultaneously, the Infrared Telescope Facility, IRTF, in Hawaii, operating on an automated schedule, logged a temperature spike from the same sky coordinates. Surface brightness temperatures on the object rose to nearly 520 Kelvin, far exceeding what solar heating alone could explain at a distance of 1.36 astronomical units. Then, just as abruptly as it began, the signature faded. Within 15 minutes, the readings returned to baseline. No gradual cooling curve, no lingering emission, It was as if the source of the heat had switched off. At first, astronomers assumed it was a data glitch, cosmic rays, calibration errors, sensor noise. But when they compared timestamps, the events lined up across 3 separate observatories: SOHO, IRTF, and ESA's Solar Orbiter SPICE spectrograph. Each instrument had seen the same phenomenon at the same moment. In observational science, coincidence across wavelengths means one thing: reality. The spectral analysis added another twist. Instead of showing broad absorption lines typical of dust or gas, the perihelion flash produced a narrow reflectance peak centered near 480 nanometers, a blue-shifted band associated with highly reflective, possibly metallic surfaces. For natural comets, perihelion usually unleashes chaos: jets of vapor, debris clouds, photometric chaos. For 3I Atlas, it was the opposite: a single, concentrated moment of radiance, geometrically precise. NASA's Jet Propulsion Laboratory later reconstructed the sequence frame by frame. The flash coincided perfectly with the moment of maximum solar alignment, when the Sun, the object, and Earth briefly formed a straight line. The reflected light curve suggested an oriented surface, one that momentarily faced the Sun directly before rotating away. If 3I Atlas was tumbling, the odds of such alignment were astronomically small. Something about its orientation seemed deliberate. Within hours, internal message boards lit up with debate. Some argued for a natural explanation. Perhaps a buried pocket of volatile material suddenly vented, exposing a fresh reflective ice sheet that caught sunlight for a few minutes before darkening. Others countered that no gas or dust increase followed. A real vent should have left a plume. The infrared spike indicated an active energy event, a release, not a reflection. Then came the magnetic data. The Solar Orbiter's EMAG instrument recorded a brief, localized perturbation in the interplanetary magnetic field during the same 12-minute window. The signal was tiny, barely 1 nanotesla, but it aligned perfectly with the object's projected position. It was as if something had momentarily interacted with the solar wind, conducting or deflecting charged particles. For researchers at ESA's heliophysics division, this was the most unsettling detail of all. A natural comet nucleus is largely an insulator: dusty ice and porous rock. To generate a magnetic disturbance, a conductive structure must exist, at least temporarily. Whether that structure was exposed metal, ionized plasma, or something stranger, no one could say. By November 2nd, the event was officially designated in internal logs as PF1, the Perihelion Flash. Reports circulated quietly between agencies. Publicly, NASA issued a vague statement. Transient reflectivity event detected during perihelion passage under analysis. But privately, the tone was different. The modelling team in Pasadena described the light curve as specular, the technical term for mirror-like reflection. In astronomy, a flash like that is a signature, the universe's way of whispering that a surface, not a storm, has just spoken. The perihelion flash didn't just brighten the night sky, it illuminated a possibility few dared to voice aloud: that something aboard 3I Atlas had responded to the Sun's energy deliberately. And when the light vanished, it left behind not darkness, but a question that now haunts every observatory on Earth. Was it a natural reaction, or a signal? Before theories of propulsion, light sails, or alien technology could even be whispered in academic circles, the scientific community had to do what it always does first: remove every simple explanation. Because extraordinary data doesn't mean extraordinary causes until every ordinary possibility has been crushed under the weight of evidence. That process began in the first week of November, in labs, observatories, and mission control rooms across the world. The first suspect was instrument error. It always is. A cosmic ray strike on a detector can mimic movement. Thermal expansion in a telescope mount can cause subpixel shifts. Even slight synchronization errors between observatory clocks can twist an orbit into a phantom curve. So engineers at NASA's Jet Propulsion Laboratory ran exhaustive calibration routines on the Punch satellite's Wide-Field Imager 3, the instrument that first detected the acceleration. They injected synthetic data, simulated cosmic noise, and ran blind reprocessing to see if the anomaly could be manufactured. The result? The deviation persisted no matter what assumptions were changed. It wasn't. A hardware illusion? Next came solar radiation pressure, the gentle push from sunlight itself. every body in the solar system experiences it, but for a natural comet to gain that much acceleration, it would have to be absurdly lightweight, almost hollow, and extremely reflective. When researchers plugged in the known reflectivity of cometary material, the numbers missed the mark by a factor of 12. 3R Atlas simply didn't have the physical properties required to move that much under light alone, unless its surface area was dramatically larger than expected, which would imply panels or sails. But before jumping to conclusions, the teams turned to the old culprit, outgassing. Outgassing, the rocket effect of vaporizing ice, explains most deviations in comet motion. When solar heat penetrates the crust, trapped gases vent outward, creating microjets that nudge the nucleus. So scientists examined spectroscopic readings from the James Webb Space Telescope and the Very Large Telescope in Chile, looking for signatures of water, carbon monoxide or carbon dioxide. There were traces of all three, but far too little. The measured gas flux was more than an order of magnitude lower than what would be required to generate the recorded delta V. Even stranger, the gas flow direction didn't match the vector of the acceleration. The thrust was pointing away from the sun, while the detected emissions were largely isotropic, spraying in all directions. That ruled out venting as the main driver. Then came thermal modelling. Maybe the object had uneven heating, one side absorbing more energy and re-radiating it asymmetrically, like a slow photon engine. Simulations tested every plausible rotation rate, shape, and composition. The models showed tiny fluctuations, but nothing that matched the clean, steady push in the data. Natural bodies produce jittery, chaotic accelerations. This one was steady. Finally, scientists considered gravitational interference, the possibility that the anomaly was an illusion caused by perturbations from unseen mass. Could an asteroid, a passing debris cluster, or even an error in solar mass constants create the discrepancy? The answer, after recalculation using refined ephemerides, was no. The gravitational model fit perfectly for every other tracked object in the same region. The anomaly was exclusive to 3I Atlas. In an effort to find something, anything, mundane, the European Space Agency even checked for software bugs in orbital prediction software. Code audits found nothing. The same open-source algorithms used to track thousands of asteroids behaved flawlessly everywhere else. One by one, the explanations fell away like layers of protective paint. By the end of that week, the teams had ruled out every common mechanism. No sensor glitch, no miscalculation, no random jet, no dust plume, no gravitational distortion. What remained was an acceleration pattern that aligned with the laws of motion, but lacked a known source of force. An engineer from ESA phrased it best in his internal report. If this were a spacecraft, the data would make perfect sense, but since it isn't supposed to be one, it makes none. That line, meant as dry humour, spread quietly among research groups, because it summarised the problem perfectly. Every test to prove 3I Atlas Ordinary had failed. The simplest explanations were gone, and what remained was the impossible. An object accelerating with purpose but without cause. In science, that's the moment where the tone changes. When equations are exhausted and the data refuses to bend, the question stops being what went wrong and becomes what if nothing went wrong at all. At first, the data seemed chaotic, a scatter of numbers, each shaped by instrumental noise, atmospheric distortion, and solar interference. But hidden within that randomness was a rhythm, faint and persistent, like a heartbeat inside static. It was this rhythm that turned the anomaly from curiosity into evidence, because while randomness can deceive, pattern rarely lies. Every observatory tracking 3I Atlas had its own data signature. Chile's readings were optical, Hawaii's were infrared, ESA's solar orbiter relied on ultraviolet flux, and NASA's Punch satellite measured brightness variation. When analysts at the Minor Planet Center stacked all those time series together, a subtle alignment began to emerge. The spikes of increased brightness, the minor positional shifts, the infrared pulses, all occurred at regular intervals, specifically every 47 minutes. It was too precise to be random. Solar activity doesn't oscillate in 47-minute cycles, nor do natural cometary jets fire that consistently. Yet the pattern repeated through multiple datasets gathered from different instruments. Something about 3I Atlas was pulsing. The next question was obvious. What could create periodic acceleration without visible exhaust? NASA's heliophysics division began correlating the object's light curve with the solar environment. They discovered that the peaks coincided with small fluctuations in solar wind density, not perfectly, but consistently enough to suggest a relationship. When the Sun's charged particle flux increased, 3i Atlas responded with a fractional change in trajectory. It wasn't reacting to heat, it was responding to pressure. In plasma physics, such a correlation implies coupling, when an object interacts electromagnetically with its environment. But natural comets don't couple with the solar wind. They're largely neutral, their gases too diffuse to sustain long-term charge separation. To couple, an object must carry conductivity or generate magnetic fields. Either scenario implied a degree of internal structure. Researchers from the European Space Agency's Plasma Physics Division simulated a conductive body passing through a variable solar wind stream. They modelled a metallic surface with residual magnetization, not enough to behave like a full magnet, but sufficient to create Lorentz forces as the charged plasma swept past. The result was a near-perfect match for the micro-acceleration curve observed in the data. It explained the smoothness, the repetition, and even the orientation of the anomaly. Still, it was speculation until proven. To confirm the pattern, astronomers turned to signal analysis. They removed every known interference, telescope jitter, Earth's rotation artifacts, background starlight, even cosmic ray hits. What remained was a clean, repeating pulse in both photometry and motion, subtle but stable. Some began referring to it informally as the Perihelion oscillation. The implications were unsettling. The pattern implied feedback, as if 3i Atlas wasn't merely affected by the Sun, but actively adjusting to it. A natural body simply absorbs and radiates energy. A controlled system, however, could modulate its response to maintain equilibrium. That's exactly what the data looked like: equilibrium corrections. During a private symposium at the Harvard-Smithsonian Center for Astrophysics, the data visualization was projected onto a large screen, a sine-like curve repeating perfectly over a 6-hour window. The room fell silent. Then Avi Loeb, the physicist who had once suggested that Oumuamua might have been artificial, leaned forward and asked one question that no one could answer without unease. What natural process repeats on a 47-minute clock? No one replied, because in the universe of random collisions and chaotic jets, regularity like that doesn't just happen, it's commanded. Over the following week, additional observations extended the dataset, and the same rhythm persisted, amplitude fading slightly as the object drifted away from the Sun, but the timing constant. It was as if 3i Atlas carried an internal metronome unaffected by external noise. By mid-November, the team submitted their findings to the International Astronomical Union under the reserved title Temporal Periodicity in C2025 N1. The phrasing was cautious, clinical, and intentionally vague. But those who had seen the raw data knew the subtext. This wasn't noise anymore, it was structure. And somewhere, 203 million kilometers from Earth, that structure was still ticking. A rhythm embedded in light and motion, whispering that behind the noise, something about 3i Atlas was alive with pattern. If light is the universe's language, then polarization is its accent. The subtle twist that reveals how it was scattered, reflected, or absorbed before reaching our eyes. For decades, astronomers have used polarization to decode what celestial bodies are made of. Dusty comets scatter light one way, metallic asteroids another. But in early November 2025, when telescopes began measuring the polarization signature of 3i Atlas, just after its perihelion passage, the results didn't fit any known accent in nature. It was as though the light itself had changed dialect mid-sentence. The first anomaly came from the Hubble Space Telescope's advanced camera for surveys, operating in polarimetric mode. During pre-perihelion tracking, 3i Atlas displayed what everyone expected: a mild negative polarization, meaning the reflected light waves were slightly more aligned parallel to the incoming sunlight, standard behavior for dusty, irregular surfaces coated with ice and carbon compounds. But less than 24 hours after perihelion, Hubble's next set of exposures showed the impossible. The polarization flipped from negative to strongly positive, exceeding 112%. To anyone outside the field, that might sound minor. But to polarization specialists, it was the equivalent of watching water flow uphill. Positive polarization means light waves are oscillating perpendicular to the incoming sunlight, something only smooth, organised or metallic surfaces tend to cause. Nature doesn't make those on comets, engineers do. To rule out a calibration mistake, the data was sent to the European Southern Observatory's VLT in Chile, equipped with its Force 2 polarimeter. 2 nights later, their measurements confirmed the same trend. A clean flip in the polarization vector, occurring precisely during the window when the brightness spike and microacceleration had been recorded. The probability of instrument error was effectively zero. At that point, the working theory shifted from why is it brightening to what just reoriented. In comets, light polarization depends on the size, shape, and composition of dust grains. When a comet vents gas, its dust environment changes, altering the polarization slightly. But 3i Atlas had shown no significant dust emission before or after perihelion. The brightness increased, but the coma, the hazy envelope around its nucleus, remained faint and compact. The polarization, however, jumped like a switch had been flipped. Dr. Meilin Zhao of the National Astronomical Observatory of Japan led one of the first comparative analyses. Her team noticed that the positive polarization correlated with an increase in the blue spectral band, a combination rarely seen except in highly reflective metals or engineered surfaces. She described it as optically coherent reflection, the kind you'd expect from parallel microstructures, panels, ribs, or even layered films. If it's natural, she said during a closed seminar, it's the most organized natural structure we've ever seen. NASA's infrared telescope facility on Mauna Kea added another piece. Infrared polarization remained almost flat. No thermal echo, no hot dust signature. That suggested the effect wasn't thermal scattering but geometric reflection. In other words, light wasn't being absorbed and re-emitted, it was bouncing. The data made one more thing clear. The polarization flip aligned perfectly with the 12-minute perihelion flash. In every model, the flash marked the same moment the reflected light became more organized, as though the surface of 3i Atlas had changed orientation. Some hypothesized that layers of volatile ice might have sublimated, exposing a denser, glassy crust beneath. Others argued that this crust would have fractured under stress, not become more uniform. A small group, led by A.V. Loeb and 2 independent plasma physicists, proposed something more radical, that 3i Atlas possessed adaptive geometry, a structure capable of aligning to incoming solar radiation. To test this, polarization data was plotted over time. The vector angle of the reflected light rotated systematically, a full 32 degrees over 6 hours, consistent with a controlled reorientation, not random tumbling. It was as if the object adjusted itself in relation to the Sun, maintaining optimal reflective efficiency. When the International Polarimetry Consortium met to discuss the findings, the consensus was cautious but unprecedented. Their final statement read, "Observed polarization inversion and subsequent stability in C2025N1 are inconsistent with standard cometry behavior. No known natural mechanism reproduces the amplitude, coherence, or timing of the effect." Behind the measured language, the implication was clear. Something on or within 3i Atlas had organized light, deliberately or through physics we don't yet understand. Polarization isn't just color or brightness, it's structure. It's the fingerprint of form, the subtle sign of design in chaos. And for 12 silent minutes during perihelion, 3i Atlas printed a fingerprint that looked engineered, a precise, mathematical reflection of intent carried on a beam of sunlight. Brightness is supposed to be predictable. When a comet draws near the Sun, heat vaporizes surface ice, dust lifts into space, and the object grows steadily more luminous. It's a process so well understood that astronomers can often sketch the entire brightening curve weeks in advance. But when 3i Atlas approached perihelion, the pattern broke. The increase in light was too steep, too clean, and too controlled to belong to something chaotic and natural. In the final nights before perihelion, telescopes around the world were tracking its glow against the background stars. At first, the brightness rose at a modest pace, exactly what every comet does when the Sun begins to warm its surface. Then, over the course of 2 days, the light curve steepened dramatically. Within 48 hours, 3i Atlas appeared dozens of times brighter than expected. Yet the coma surrounding it, the faint mist of gas and dust that should have expanded outward, remained small and perfectly defined. The anomaly was first flagged by a photometry team in Chile, who thought the readings were corrupted. They checked their calibration, reprocessed the data, and found no error. Then the same pattern emerged in independent observations from Hawaii and Japan. When the measurements were plotted together, the rise in brightness formed a near vertical line before flattening at perihelion, then descending smoothly afterward. The shape of that curve matched no known cometary behaviour. Under ordinary circumstances, a brightening like this would mean an explosive outburst. Volatile gases escaping, surface layers fracturing, dust scattering sunlight in every direction. But 3A Atlas showed no sign of violence. The increase was uniform, as if the entire surface had become more reflective at once. To the astrophysicists reviewing the graphs, it looked less like an eruption and more like a transformation. Spectral analysis deepened the mystery. The colour of the reflected light shifted away from the warm reddish hue typical of dusty comets toward a colder silvery tone before gradually returning to normal. Such a transition usually indicates a change in particle size or composition, but there was no evidence of new dust production. It was as if the surface itself had altered its optical texture, becoming smoother, glossier, almost metallic, then reverted once the object moved farther from the sun. Models of normal cometary activity could not reproduce this behaviour. When researchers adjusted variables, dust grain size, rotation rate, ice composition, sublimation depth, the simulated light curves always produced noise, flicker, and irregular jumps. The real data was the opposite, a smooth mathematical progression that obeyed geometry, not randomness. It resembled the signature of a surface turning toward the sun to maximize reflection, holding that orientation, then slowly relaxing back. Some observers described the effect as mirror-like. The phase angle dependence, the relationship between how sunlight strikes an object and how bright it appears from Earth, showed a sharp peak at a very specific angle, consistent with specular reflection from a flat or curved surface. Dust can scatter light, but it cannot focus it. Only something structured can do that. NASA's internal summary called it the brightness event. Their report avoided speculation, but a line buried near the end revealed the scale of the puzzle. The object's effective reflectivity had increased by several factors during the peak. That kind of change would require the sudden exposure of a vast, highly reflective region, something the size of a mountain opening like a mirror to the sun. To those following the story, the implication felt uncomfortably deliberate. The increase in brightness matched the timing of the perihelion flash and the recorded acceleration, forming a chain of events too precise to ignore. Heat, light, motion, all peaking in synchrony, as though 3I Atlas had responded to the sun in real time. The official explanations, surface ice, vapor pressure, subsurface venting, remained on the record. But off the record, a quieter theory circulated that this wasn't simple reflection, it was reaction. The interstellar visitor had not merely brightened, it had activated. When something in space brightens, the first question astronomers ask is simple: what's burning? Every glow tells a story through its spectrum. Heated gases sing in colour, each element revealing itself through sharp, distinct lines. Water vapour hums in the infrared. Carbon monoxide whistles in the ultraviolet. Metals leave their fingerprints in visible light. Even chaos has order when seen through a spectrograph. But when the instruments turned toward 3I Atlas during and after its perihelion event, they heard nothing. No emission lines, no chemical whispers, just silence. It was the James Webb Space Telescope that confirmed it first. Positioned perfectly beyond Earth's atmosphere, Webb recorded the object across the near and mid-infrared bands, searching for molecular signatures, the telltale traces of gas venting from a warming surface. Every other comet observed under similar conditions had produced a spectrum filled with peaks and valleys, evidence of volatile compounds being released as sunlight baked their frozen crusts. But 3 Atlas returned a featureless slope. It reflected sunlight, yes, but it emitted nothing of its own. The data puzzled everyone. Natural outgassing creates noise, thermal radiation, faint dust scattering, sublimation trails. Silence like this was impossible for an object so close to the sun. It was as if the heat that should have torn it apart had been absorbed without reaction. The European Southern Observatory ran a follow-up study using their optical spectrograph on the Very Large Telescope in Chile. The expectation was clear. If Webb's infrared silence was real, optical wavelengths might still reveal dust or plasma emission lines. sodium, calcium, maybe ionized carbon. But the spectrum was just as empty. No new bands appeared, no shifts, no broadening. The light coming from 3i Atlas wasn't being generated, it was being reflected with surgical precision. That realization sent a chill through the community. Reflection without emission is not typical for rough, dusty comets. Even the most inert asteroids show faint absorption dips caused by minerals or surface weathering. 3i Atlas, in contrast, displayed a mirror-like purity, a continuous spectrum matching solar radiation almost line for line. Scientists began using a phrase they hadn't touched since the debates around Oumuamua: specular consistency. It meant that the light from the object matched the sun's signature so perfectly that the difference between the two was nearly indistinguishable, as though sunlight was being bounced back by a flawless surface. That level of precision is nearly impossible to find in nature. NASA's Heliophysics division conducted another experiment, comparing the sun's incident spectrum with 3i Atlas's reflected signal. Even after correcting for Doppler shift, the two curves overlapped by more than 99%. There was no detectable reprocessing of energy, no color change, no absorption features, no fluorescence. It was as though 3i Atlas was a perfect mirror, incapable of absorbing light or converting it into heat. That last detail was the most disturbing. Infrared observations from both Webb and ESA's solar orbiter thermal sensors showed that the object's temperature dropped immediately after perihelion, rather than lingering warm as expected. Every known material, rock, ice, metal, holds residual heat. But 3i Atlas cooled instantly, like a body that refused to retain energy at all. For weeks, the data teams tried to fit the observations into known models. Maybe the angle of reflection masked the thermal emissions. Maybe the dust grains were unusually large and non-emissive. Or perhaps, as one internal memo dared to suggest, the reflective properties are not passive but regulated. The phrase was cautious, almost reluctant. To regulate reflection would imply awareness, a capacity to alter optical behaviour based on external input. Meanwhile, at the University of Cambridge, a team specialising in light polarisation performed a more granular breakdown. They separated the solar component from the reflected component, expecting random scatter. Instead, the light returned with phase coherence, meaning the waves were still partially ordered. In simple terms, the light hadn't just bounced, it had been managed. The findings left researchers with two possibilities. Either 3i Atlas was composed of a substance we have never seen, a natural material capable of nearly perfect reflection and instant cooling, or it was something far less natural, a structure designed to handle energy rather than endure it. In astronomy, silence can mean failure, a gap in data, an instrument malfunction, a misreading of noise. But this silence was different. It wasn't absence, it was precision. The spectrum of 3i Atlas wasn't missing information, it was refusing to speak. And for scientists trained to decode the voices of the cosmos, that refusal was more haunting than any noise. When the first reports of unexplained acceleration began circulating, most scientists hesitated to use the phrase light sail. It sounded like science fiction, a metaphor better suited for novels than peer-reviewed papers. But as the silence in the spectrum deepened, and the brightness data aligned perfectly with solar illumination, the comparison became unavoidable. If 3i Atlas wasn't venting gas, wasn't heating up, and wasn't fragmenting, then the sun itself might be the engine. The concept of a light sail is simple in theory and breathtaking in practice. Photons, though massless, carry momentum. When they strike a reflective surface, they impart an almost imperceptible push. Over time, that push can accelerate an object across space without fuel, without exhaust, powered only by starlight. The Japanese mission, Ikaros and the Planetary, Society's light sail projects had already demonstrated the physics on a small scale. Thin, gleaming sheets of polymer unfurling in the solar wind, drifting silently through sunlight. 3i Atlas behaved as if it understood that principle intimately. The acceleration vector pointed exactly away from the sun. Not random, not chaotic, but geometrically precise. The rate of acceleration mirrored the intensity curve of solar flux, increasing as radiation pressure peaked and tapering as the object moved outward. The symmetry was uncanny. Dr. Avi Loeb, who had once proposed that Oumuamua might have been propelled the same way, found his earlier work suddenly relevant again. His team at Harvard ran a series of updated models using the observed motion of 3I Atlas. To reproduce the measured velocity change, a light sail-like structure would need to have an extraordinary area-to-mass ratio, thin enough to catch photons yet strong enough to survive near solar radiation. When they input those parameters, the simulation matched the trajectory almost perfectly. The data fit was so close that one researcher remarked, "It's as if someone engineered it to teach us this equation." Of course, that idea came with resistance. Natural explanations were still being pursued aggressively. Could 3I Atlas simply be a fragment of some low-density material, perhaps a chunk of frozen aerogel from a disrupted exoplanet? Could its surface be naturally laminated by unknown interstellar chemistry, forming a reflective sheet that coincidentally mimicked the mechanics of a sail? The odds were remote, but not zero. The challenge was that no known natural process could create an object with such uniform thickness and such a stable orientation under solar pressure. Astronomers began to scrutinize the object's rotational behavior. If it were truly a thin sail, its spin should be minimal. Angular momentum would destabilize reflection efficiency. Observations from the Hubble Space Telescope suggested precisely that. 3I Atlas exhibited a remarkably consistent light curve, showing almost no variation in brightness over multiple rotations. That meant it wasn't tumbling chaotically. It was holding attitude, keeping one face aimed at the sun like a sunflower tracking light. Meanwhile, ESA's solar orbiter provided an unexpected clue. Magnetometer readings showed a faint rhythmic fluctuation in the local solar wind, synchronized with the object's position. The pattern looked like interference, as though charged particles were being reflected or deflected by a broad conductive surface. Plasma physicists noted that this was exactly what a metallic sail would do, not only capture photons, but also repel high-energy ions. By late November, the phrase light sail hypothesis re-entered scientific vocabulary, not as speculation but as a legitimate line of inquiry. Papers with cautious titles, Non-Gravitational Forces and Reflectivity in 3I Atlas, and Photonics, Pressure Coupling in Interstellar Objects, began circulating in preprint archives. The wording was careful, almost apologetic, but the meaning was clear. The object's behavior aligned more closely with controlled reflection than with any natural process. For many, this was the most thrilling and terrifying possibility. If 3I Atlas was indeed propelled by light, two conclusions followed. Either nature had somehow created a perfectly tuned solar sail out of cosmic debris, or something intelligent had done it deliberately. At the Harvard-Smithsonian Center for Astrophysics, one evening discussion ended in silence after a young researcher summed it up in a single sentence. If the sun is pushing it and it's steering, then someone built it. No one argued. The data had made its case. Revisiting the light sail hypothesis didn't just reopen an old debate, it reframed the entire meaning of motion in space. For the first time since humanity began charting the heavens, an interstellar object was acting not like a passenger of gravity, but like a vessel under power. And that quiet realization that something out there might have mastered the art of sailing on sunlight changed the way every scientist looked at the empty space between the stars. By early November, every observatory involved in tracking 3I Atlas was being forced to confront an uncomfortable truth. The data could no longer be dismissed as coincidence. Yet before anyone could claim the object had responded to sunlight, the scientific method demanded something more absolute. Proof through elimination. Every anomaly must be tested against a control. So the world's instruments were pointed not just at 3I Atlas, but at other perfectly ordinary bodies moving through the same region of space. If the same sensors picked up nothing unusual elsewhere, then the anomaly was genuine. If they did, it was an artifact. The experiment became known informally among astronomers as the control run. NASA's Punch satellite began the procedure. Its wide-field imager recorded 3I Atlas daily, logging position and brightness while simultaneously capturing nearby asteroids and comets as comparison targets. One of those was C2024 K3, a conventional comet with a well-known composition and stable orbit. The same instruments, same exposure settings, same background correction, yet K3's readings matched every model perfectly. No unexplained acceleration, no reflectivity spike, no spectral silence. Only 3I Atlas continued to defy prediction. Next, The Very Large Telescope in Chile repeated its polarimetry tests on a reference object located only a few degrees away in the sky. It showed the expected negative polarization, behaving exactly like dusty sunlit ice should. But when the telescope pivoted back to 3I Atlas, the positive polarization signature reappeared, stable, coherent, and impossible to mistake. At the European Space Agency, engineers ran a deeper, calibration audit. Every variable that could bias readings, CCD temperature, sensor alignment, timing offset, pointing error, was tested in isolation. They even simulated the conditions of perihelion using data from earlier missions, feeding false coordinates into the same pipeline to see if the same ghost acceleration would emerge. It didn't. The anomaly existed only when 3I Atlas entered the frame. Even amateur astronomers joined the effort. Dozens of backyard observatories across Europe and Asia contributed photometric readings, using off-the-shelf telescopes and standardized filters. Their measurements were crude compared to the professional datasets, but the result was consistent. Whenever 3I Atlas was visible, its brightness jumped higher than predicted. Neighboring stars and calibration targets remained perfectly stable. The Jet Propulsion Laboratory's navigation team took the testing further. They reran the orbital models with intentionally corrupted data, removing points, shifting timestamps, exaggerating uncertainties, to see whether the strange motion could be an artifact of statistical noise. No matter how the inputs were altered, the residual acceleration remained. It was baked into reality. By mid-month, the last major crosscheck came from ESA's solar orbiter, which compared magnetometer data across multiple solar longitudes. If the object's push were caused by a broader solar event, the same magnetic fluctuations would appear elsewhere in the field, but they didn't. The disturbances followed 3I Atlas alone, as if the object carried its own invisible bubble of interaction with the solar wind. All of this evidence was compiled into a single technical document shared quietly among agencies. Control tests performed on adjacent celestial bodies and synthetic datasets confirm that the observed non-gravitational acceleration, reflectivity enhancement, and polarization inversion are intrinsic to 3I Atlas. Instrumental or environmental contamination ruled out with 99.8% confidence. The language was cold, mechanical, but the implications were anything but. Behind closed doors, the scientists admitted what the controls had proven. Every sensor on Earth and in orbit had passed the test. The universe itself had been the experiment. And the result was unambiguous. Only one object, a visitor from interstellar space, was behaving as if the sun's light was more than illumination, as if it was fuel. Dr. Eleanor Chandra, part of the Solar Physics Division at Goddard, summarized the quiet astonishment of her peers. We did everything right. We tested the sky against itself, and the sky told us the same story. With the controls complete, the debate could no longer hide behind instrumentation or coincidence. The anomaly belonged to 3I Atlas alone, an object that obeyed every physical law, except the one that says motion requires mass to be spent. For the scientists who had spent their careers trusting equations, this was the moment the math began to feel alive. Every object that passes near the sun must face the same trial: heat. It's the oldest law in the solar system. Sunlight strikes, temperature rises, matter responds, ice vaporizes, dust expands, rocks glow red before cooling again. Energy always leaves a trace. But in the case of 3I Atlas, there was no trace at all. When the interstellar object swung through perihelion, every observatory expected to see the familiar infrared crescendo that accompanies solar heating. Even a small asteroid will radiate detectable warmth as it absorbs sunlight and re-emits it in longer wavelengths. Instead, the data came back flat. No thermal echo, no residual glow, nothing resembling the radiative lag that every known material exhibits. The first team to notice this absence was operating NASA's Infrared Telescope facility in Hawaii. They monitored 3I Atlas for hours, taking continuous readings before, during, and after its closest pass to the sun. The telescope's instruments are so sensitive they can detect the cooling rate of volcanic lava on distant moons. Yet here, the signal barely moved. The temperature spiked briefly during the perihelion flash, then plunged to background levels almost instantly. That instant cooling defied every expectation. Even a mirror reflects only part of the light that hits it. The rest becomes heat. A thin layer of ice would sublimate, a metal would retain warmth for hours, a dust crust would emit a gentle infrared hum. But 3i Atlas radiated nothing. It was as if it had swallowed the sun's energy and left no footprint behind. To confirm the finding, the James Webb Space Telescope was enlisted. Webb's mid-infrared instrument can measure minute thermal variations down to fractions of a degree. The expectation was simple. If the object's surface had heated at all, Webb would see it. The data arrived as a near-perfect horizontal line. No curve upward, no slow fade, pure equilibrium. The absence of heat puzzled even the skeptics. One possibility was geometry. Perhaps the object's reflective surface redirected sunlight so efficiently that almost none of it was absorbed. But that would require a precision of alignment difficult to maintain for a natural tumbling body. Another idea suggested that the surface was covered in an unknown dielectric material, something capable of reflecting light across nearly all wavelengths without internal absorption. In laboratory physics, that kind of material exists only in prototypes, thin photonic films engineered for experimental spacecraft. The European Space Agency's thermal modelling group tried to build a natural explanation. They simulated an ultra-porous carbon-silicate mixture that could dissipate heat through internal radiation rather than surface conduction. The model did cool faster than rock or ice, but not instantaneously. No matter what assumptions were applied, every known substance still held warmth for minutes or hours. As the simulations failed, attention turned to a different possibility: active heat management. If 3i Atlas possessed the ability to channel absorbed energy away from its surface, perhaps through electromagnetic coupling with the solar wind, the observed cooling could make sense. Plasma physicists noted that the brief magnetic fluctuations recorded during the perihelion flash matched what might happen if charged particles were being deliberately deflected, carrying thermal energy off with them. It was speculation, but it was the first hypothesis that didn't collapse under its own math. Dr. Amira Torres at ESA phrased it carefully in her internal memo. The object's thermal response is inconsistent with passive reflection or conduction. The data suggest an active equilibrium mechanism, an ability to regulate temperature dynamically rather than radiate it. Her colleagues softened the wording before publication, replacing regulate with mediate. But the idea lingered. Regulation implied intent, the possibility that 3i Atlas didn't just endure solar heat but managed it. By mid-November, the term the thermal question had entered the quiet vocabulary of scientists tracking the anomaly. It summed up the single mystery that seemed to tie all the others together: the brightness without heat, the acceleration without exhaust, the flash without flame. If 3i Atlas was a comet, it should have boiled. If it was a rock, it should have baked. Instead, it behaved like something that understood the sun, not as an enemy to survive, but as a force to balance. And in that calm defiance of thermodynamics, 3i Atlas once again reminded us how fragile our definitions of natural truly are. In science, context is everything. A single measurement means little without a comparison, a control, a neighbour, a reference frame. So when the data from 3i Atlas began to strain the limits of known physics, astronomers searched for something nearby that could anchor their understanding. That anchor became Venus. In the days following perihelion, 3i Atlas crossed an orbital corridor not far from the orbit of Earth's sister planet, close enough that instruments monitoring Venus could also catch faint echoes of the interstellar traveller's passage. Venus is one of the best-studied worlds in the solar system, a planet whose atmospheric brightness, thermal output, and reflective behaviour have been mapped down to the decimal. That made it the perfect benchmark. If the sensors saw anything odd near Venus that matched what was seen with 3i Atlas, then perhaps the anomaly wasn't unique after all. The first to notice something strange was ESA's solar orbiter, whose instruments continuously record sunlight reflected off Venus's dense cloud deck. On November 3rd, during a routine scan, the orbiter detected faint reflective glints at coordinates that didn't match any atmospheric event or satellite artifact. They were brief, regular flashes, so subtle that early reviewers dismissed them as cosmic ray interference. But when the timestamps were compared to 3i Atlas's trajectory, the glints aligned perfectly with its projected path across the ecliptic. That coincidence was impossible to ignore. Venus provided a background canvas of stable, predictable light, Any deviation stood out like a heartbeat in silence. By isolating the reflected sunlight from the planet and comparing it with the glints attributed to 3I Atlas, scientists discovered that the interstellar object's reflective signature was far more coherent, sharper, narrower in wavelength, almost laser-like in its consistency. Venus, by contrast, scattered light diffusely, as expected from thick clouds of sulfuric acid droplets. The difference was so stark that the analysts began referring to the two signals as diffuse Venus and structured Atlas. The Bepi-Colombo mission, orbiting near Venus for its own gravitational assist, provided additional evidence. Its onboard magnetometer recorded weak disturbances in the solar wind at nearly the same time as the reflective glints. The pattern was localized, fading as 3I Atlas receded from Venus's orbital plane. There was no corresponding magnetic event near the planet itself. That suggested the disturbances were caused not by Venus's ionosphere, but by the passing interstellar object. Meanwhile, ground-based telescopes compared Venus's albedo, its natural reflectivity, with the temporary bright point observed in its vicinity. Venus's reflected sunlight changes predictably with its phase angle. The anomaly did not. The object's reflectivity remained constant even as its orientation relative to both the Sun and Earth shifted, implying either a fixed, stable geometry or an active adjustment mechanism maintaining a constant optical cross-section. By now, astronomers were treating Venus as a living calibration target. They used it to test everything: brightness algorithms, phase angle corrections, atmospheric scattering models. Each adjustment confirmed the same conclusion: the sensors were functioning perfectly. The comparison stripped away the last hope of blaming instrumentation. The Venus baseline report circulated among NASA, ESA and JAXA scientists summarized the findings with clinical precision. Comparative photometric analysis between C2025, N1, 3I Atlas, and Venus reflectivity curves indicates non-atmospheric reflectance coherence unique to the interstellar object, instrumental and environmental influences excluded. In simpler terms, the nearby planet behaved exactly as it always had. The visitor did not. For some, this baseline brought relief. It proved their instruments were sound. For others, it deepened the unease. The Venus comparison revealed not an illusion, but contrast, the clear separation between what's natural and what's engineered. Dr. Luis Moreno at ESA described it best. Venus showed us what sunlight normally does when it meets matter. Atlas showed us what sunlight can do when matter decides to answer back. After that, the Venus baseline became more than a technical benchmark. It became a metaphor, the line between the known and the unknown, between a planet we understand completely and a traveller we understand not at all. Venus had been the mirror for our certainty. 3I Atlas, the crack in that mirror, reflecting something we had never seen before. Light shaped not by chaos but by control. When the data on 3I Atlas first poured in, the acceleration without exhaust, the perfect reflectivity, the silence in the spectrum, scientists did what scientists always do. They built models. They fed equations with everything we know about how light, gas, dust, and heat behave in the vacuum of space. They let the computers run, expecting that somewhere, in the billions of permutations, nature would reveal its trick. But the simulations all failed in the same way. At NASA's Jet Propulsion Laboratory, the initial modeling campaign began with a simple premise. If 3I Atlas was behaving like a comet, then outgassing must be the answer. The team coded sublimation dynamics for water, carbon monoxide, and carbon dioxide, the three most volatile ices known to exist on comets. They added rotation, surface irregularities, variable densities, even fractures that could vent gas in bursts. The result was always the same. The model produced noise, jitter, tiny wobbles in acceleration that never lined up with the smooth, steady motion recorded in the real data. So they tried a different path: dust reflection. Could micron-sized particles forming a dense coma around the object produce the unusual brightness and polarization readings? Again, no. In every scenario, the dust created random scattering, diffusing light in all directions. The observed behavior of 3I Atlas was the opposite: coherent, directional, and stable. Dust cannot act like a mirror. At the European Space Agency, a separate group attempted thermodynamic modelling. If the object were made of a porous composite, perhaps the heat of the sun penetrated deep within, releasing vapour through unseen fissures that balanced each other's thrust. It was an elegant idea, a network of natural vents providing controlled acceleration. But even with perfect symmetry, the model couldn't replicate the precision of the real trajectory. Nature doesn't engineer balance, it favours chaos. When those efforts failed, physicists turned to exotic materials. They imagined an interstellar body composed of carbon nanostructures, or a hollow aggregate of molecular ices laced with metals, perhaps formed in the violent debris of a supernova. Supercomputers ran for days, crunching possibilities. The outputs all broke under the same constraint: thermal stability. Anything light enough to accelerate as 3I Atlas did should have been torn apart by radiation pressure near the Sun. Anything strong enough to survive would have been far too massive to move the way it did. That paradox, light yet resilient, stable yet reactive, became known among the researchers as the Atlas Gap. Between those two conditions, no known natural material could exist. The Harvard-Smithsonian Center for Astrophysics took a more radical approach. Instead of assuming 3I Atlas was a solid body, they modelled it as a distributed electromagnetic structure, a field object interacting with the solar wind. In these simulations, magnetic pressure replaced gas thrust. The results came close to the observed acceleration, but only under implausible assumptions: a perfectly aligned magnetic dipole, steady field strength, and continuous self-correction. When the parameters were loosened, the behaviour collapsed. Nature doesn't self-correct that precisely. Even artificial light sail models struggled. A purely passive reflective surface should wobble as photons strike unevenly across its surface. Yet the object's motion was flawless. No precession, no drift. To replicate that, engineers had to add control systems to their simulations: attitude stabilization, adaptive reflectivity, micro-adjustments in response to solar pressure. In other words, they had to make the sail smart. Dr. Elena Voss, a systems engineer from ESA, said it bluntly during a review session: "To make the data fit, you have to give it instincts." By late November, after countless revisions, all the major models converged on a single conclusion. The phenomenon observed in 3I Atlas wasn't impossible, just unattainable by natural physics as we understand them. The gap between observation and simulation wasn't a flaw in mathematics, it was a flaw in assumption. The equations were fine. The premise, that the object was inert, might not be. So the working group stopped trying to force a fit. The final reports used words like anomalous coherence, non-chaotic reflectivity, and non-stochastic acceleration. Each phrase was a way of saying the same thing: the models couldn't reproduce what reality had shown. And quietly, in the margins of those reports, one question began to circulate. Not publicly, not yet, but whispered in the private chat rooms where scientists let curiosity slip past protocol. What if we're not modelling a rock at all? Because in the cold logic of physics, there is only one reason a system behaves more perfectly than any model can describe. It isn't following equations, it's following design. Science doesn't break overnight, it fractures slowly. It starts with a few outliers whispering doubts, then spreads through data rooms, conference calls and private emails until the divide becomes impossible to hide. By mid-November, 3I Atlas had done more than defy models. It had divided the scientific community that studied it. At first, the debate was cautious. Words like anomaly, non-gravitational component, and reflectivity variance kept everyone on safe ground. But once the peer review drafts began circulating, those terms hardened into positions. There were now two camps. On one side stood the conservatives, the guardians of classical physics. They argued that 3I Atlas must be a natural object, a comet, an asteroid, or a piece of debris behaving oddly due to factors we hadn't yet identified. Their confidence came from precedent. Every cosmic mystery in history had eventually yielded to natural explanation. The canals on Mars, the flicker of pulsars, the radio burst from space, all had once been thought impossible. Nature is patient, wrote Dr. Anil Batra of Caltech. It allows us to be wrong before it shows us the pattern. On the other side were the revisionists, a younger, data-driven generation who saw the numbers for what they were: too clean, too precise, too deliberate. Their argument wasn't that 3I Atlas was alien, few dared to say that outright, but that it represented a new class of object altogether. something between artifact and phenomenon. To them, denying the implications of the data was less rational than accepting them. Online forums became battlegrounds. In Slack channels, long-standing colleagues corrected each other's language. "Don't say intelligent control, say stabilized response," one astrophysicist warned. Another replied, "If it looks stabilized, how long before we admit something is doing the stabilizing?" At conferences, tension thickened the air. During a joint NASA-ESA teleconference, a heated exchange between two senior scientists leaked to the press. One accused the other of romanticizing data, claiming that the entire anomaly was an illusion of measurement bias. The rebuttal was swift. Then explain why the bias obeys Kepler's laws better than Kepler's own equations. For journalists, the divide was irresistible. Headlines called it the Atlas Schism. Some media outlets painted it as a story of brave innovators challenging dogma. Others framed it as a cautionary tale of overinterpretation, a repeat of the Oumuamua hysteria. The public loved it either way. For the first time in decades, interstellar science trended on social media feeds alongside politics and entertainment. Behind the scenes, institutions began drawing invisible lines. NASA's Public Relations Office advised its staff to avoid speculative language. The European Space Agency quietly issued a memo urging scientific restraint in all interviews. Meanwhile, the Harvard-Smithsonian Center for Astrophysics doubled down, hosting internal seminars under the deliberately vague title Photonic Response in Interstellar Objects. Some researchers, overwhelmed by the scrutiny, withdrew entirely. A few even deleted their contributions from public repositories. Others embraced the uncertainty, treating 3i Atlas as an invitation to rethink the limits of celestial mechanics. Dr. Meilin Zhao, the polarization expert from Japan, summed up the divide in a single sentence. "Half of us are afraid the data is wrong. The other half are afraid it isn't." As December approached, the arguments began to sound less like scientific debate and more like philosophy. If an object could accelerate without fuel, what did that mean for conservation laws? If its surface could regulate temperature and light, what did that mean for thermodynamics? And if something, or someone, had designed it, why send it here? Even the most stoic researchers began to feel the pressure. During a closed ESA briefing, one engineer compared the controversy to the early days of quantum mechanics. "We're looking at the numbers and realizing that the universe is allowed to be stranger than we are comfortable with." By the end of November, the divide was complete. The conservative camp held to their models, waiting for time and distance to expose a natural cause. The revisionists prepared for something unprecedented, the possibility that 3i Atlas wasn't an accident of physics, but a message written in motion. And so, the community split not over what they saw, but over what they were willing to believe those numbers meant. In that rift, science did what it always does at the edge of the unknown. It argued with itself, loudly, brilliantly, and perhaps, for the first time in a generation, with genuine awe. The first rule of public science is transparency. The second is timing. NASA lives by both, or at least it tries to. But when the data from 3i Atlas began to hint at something that broke the first rule of physics, transparency suddenly became a liability. What could they say and when, without fueling panic, ridicule, or, worse, misinterpretation? By the second week of November, the agency had all the evidence it needed to know the anomaly was real. The acceleration curve, the polarization flip, the lack of thermal emission, it all checked out. Nothing in NASA's logs could explain the object's behavior with known forces or materials. And yet, when journalists asked for comment, the replies were cautious to the point of sterility. Officially, the agency's line was this: "We continue to monitor the trajectory and photometric behavior of 3i Atlas. Preliminary data suggests non-gravitational influences that remain under study." That sentence became the shield, repeated word for word across press releases, briefings, and interviews. But behind closed doors, the tone was very different. Internal Slack channels were buzzing. Engineers shared plots that looked too clean to be random. Astrophysicists quietly debated whether the reflectivity spikes implied mechanical geometry. The conversations were electric and unpublishable. The Office of Communications issued a memo reminding employees of professional discretion. It advised staff not to use terms like light sail, engineered object, or controlled motion in any written correspondence. The memo didn't forbid, Curiosity, it forbade vocabulary. The reasoning was simple. Once those words entered the public lexicon, NASA would lose control of the narrative. That caution wasn't paranoia, it was survival. The agency still bore scars from past controversies. The microbial fossils found in Martian meteorites, the arsenic life claims, even the early missteps during the Oumuamua debates. Every time speculation outpaced verification, the backlash had been brutal. Funding committees didn't like mysteries they couldn't quantify. Politicians didn't like headlines that made them sound uninformed. So NASA learned to speak softly, even when staring directly at the extraordinary. Meanwhile, researchers across its divisions, JPL, Goddard, Ames, were running quiet side analyses on personal time. The rules were clear. No unauthorized datasets, no independent statements. Yet, emails leaked. A few graphs found their way onto private astrophysics forums. Polarization curves, brightness profiles, acceleration residuals. Anonymous posts titled "The Object That Refuses to Heat" began circulating. The scientific world recognized the formatting style instantly. It was NASA's data, just stripped of its name. Within days, speculation spread faster than the agency could contain it. Every social media thread, every science podcast, every fringe blog turned 3i Atlas into an omen or a miracle. NASA's silence meant to keep the peace, only fed the storm. The less they said, the more the world filled in the blanks. Inside the Jet Propulsion Laboratory, morale was divided. Some engineers argued for openness, for publishing the anomaly outright and letting peer review do its work. Others insisted restraint was the only responsible course. One internal chat log captured the tension perfectly. "We can't confirm it's artificial," a researcher wrote. "Then what's stopping us from saying it might be?" another replied. "The internet," came the answer. The leadership sided with caution. On November 21st, the agency issued a second statement, even more neutral than the first. No evidence currently supports non-natural origin hypotheses. Further analysis is ongoing. It was a sentence built to sound final while admitting nothing. But inside NASA, no one believed it was final at all. The analysis wasn't ongoing, it was accelerating. New models, new comparisons, new observations from the James Webb Space Telescope were already being prepared. Only the language had frozen. Off the record, one senior administrator put it bluntly during a private debriefing. "The moment we say it out loud, it stops being science and becomes history." NASA's careful silence wasn't ignorance or denial, it was strategy. They weren't just protecting reputations, they were buying time. Time to test, to confirm, to understand what kind of story they were standing in before the world demanded answers. Because once the agency spoke freely, there would be no taking it back. And until they could prove whether 3i Atlas was a natural wanderer or something built to wander, silence, however uneasy, was the only language they trusted. If light and heat could not explain the motion of 3i Atlas, perhaps magnetism could. That was the thinking in late November, when a group of plasma physicists and heliophysicists convened at ESA's Operations Center in Darmstadt to examine one of the strangest signatures buried in the telemetry, a rhythmic fluctuation in the solar wind synchronized with the object's position. At first glance, it was barely noticeable. The solar orbiter's MAG instrument had recorded a brief distortion in the interplanetary magnetic field. A pulse only a few nanoteslas strong, lasting less than 20 minutes. Normally, such ripples are routine, caused by waves of charged particles from the Sun or interactions with planetary magnetospheres. But this one followed 3i Atlas across space like a shadow. It appeared, moved with it, and vanished when the object crossed a threshold of distance from the Sun. That persistence triggered what became known internally as the magnetic hypothesis. The idea was simple, yet radical. What if the object was not being pushed by sunlight, but pulled, or coupled, to the magnetic fabric of the solar wind itself? To explore this, scientists modelled 3i Atlas as a conductive body, perhaps laced with metals or ferromagnetic minerals. In the plasma environment of the inner solar system, such a body could experience electromagnetic drag or even Lorentz acceleration as it interacted with the Sun's magnetic field. It was the same principle behind experimental spacecraft propulsion systems on Earth, so-called electrodynamic tethers, which use a conductive wire to generate current as they cut through magnetic fields, producing thrust without fuel. The models worked, but only in fragments. The direction of the magnetic acceleration matched the data, but the magnitude didn't. The observed force acting on 3I Atlas was far too strong for a passive conductor. To achieve that much acceleration naturally, the object would need to generate or sustain its own magnetic field, an idea that bordered on the impossible. Still, the numbers refused to be dismissed. When the data from NASA's Parker Solar Probe was added, a second anomaly appeared, a faint oscillation in proton density near the object's projected path, suggesting it was disturbing the local plasma environment. The disturbance looked like interference, as if solar wind particles were being redirected around an invisible boundary. That finding shifted the tone of the discussions. Could 3I Atlas be carrying a residual charge from its interstellar journey? Could it have accumulated magnetized material in another system, then reawakened under the sun's influence? The equation suggested that even a small dipole moment, a leftover magnetization, could create measurable thrust under the right plasma conditions. But to remain stable through perihelion, the field would need to be self-regulating. That part made no sense. At Goddard Space Flight Center, Dr. Eleanor Chandra ran simulations coupling magnetohydrodynamics with radiation pressure. Her results hinted at a hybrid phenomenon, a body that used both light and magnetism to maintain trajectory. In her report, she described it as a system displaying dynamic equilibrium with the solar environment. In plainer terms, it was adapting. When the data reached peer reviewers, skepticism flared. Some insisted the magnetic readings were artifacts, remnants of solar interference misattributed to the object. But others couldn't ignore how precisely the field fluctuations tracked 3I Atlas's position. There was rhythm in the noise, the same pattern already seen in its periodic acceleration. That consistency raised a question no one wanted to phrase publicly. If 3I Atlas was magnetically responsive, was it also magnetically active? The difference between those two ideas was the difference between a rock and a reactor. The Magnetic Hypothesis Group, as they came to be called, submitted their findings to the International Astronomical Union under the title Plasma Interaction, observed in the vicinity of interstellar object 3I Atlas. The phrasing was conservative, but the conclusions were not. Their summary stated, data indicates a sustained coupling between C2025, N1, and the heliospheric magnetic field, producing non-random directional modulation in plasma density. The report was met with silence from official channels, and fascination everywhere else. Online, the phrase magnetic coupling spread like wildfire, attached to every theory imaginable. Some claimed the object was harnessing solar energy. Others said it was cloaked in an electromagnetic shield. For scientists, the truth was simpler and more unsettling. Magnetism had given them the first mechanism that almost made sense, yet still exceeded what physics allowed. It sat on the threshold between natural and intentional. As Dr. Chandra later admitted in a private note, if the field lines are moving with it, not around it, then it isn't drifting through the solar wind, it's sailing on it. And with that, the debate over magnetism stopped being a curiosity. It became the first real whisper of control, a force that shouldn't exist, responding to a star it had no reason to obey. The first pulse, the rhythmic brightness oscillation observed during perihelion, had been dismissed by many as coincidence, an artifact of overlapping solar noise. But when the second one came, there was no longer any room for doubt. It wasn't a coincidence, it was a pattern, and this time it seemed deliberate. The detection came from the Solar Orbiter's SWA instrument, which measures the flux of charged particles streaming from the Sun. On November 26th, just as 3I Atlas crossed the outbound corridor beyond Mercury's orbit, the instrument recorded a faint but unmistakable modulation in particle density. It wasn't random turbulence. It was pulsed, spaced evenly, each wave separated by just under an hour. The signal lasted for 6 cycles, then faded. Almost simultaneously, Earth-based observatories recorded a matching optical signature. Small, rhythmic variations in brightness, echoing the same interval. The probability of 2 independent systems producing synchronized periodic data was infinitesimally small. The conclusion was simple. 3I Atlas had pulsed again. The first time during Perihelion, researchers had blamed solar interference. The sun's radiation storm could easily have mimicked the rhythm. But this second pulse occurred in a quiet solar environment, with no coronal mass ejections, no flares, and no wind irregularities. The sun wasn't the source. Whatever was modulating light and plasma density now was originating from the object itself. At ESA's operations center in Darmstadt, the team immediately began cross-referencing the new data with previous readings. The interval between pulses was identical to the earlier 47-minute periodicity first seen near the Sun, but this time the amplitude was stronger, cleaner, more defined. It wasn't just repeating the earlier pattern, it was amplifying it. That was the moment when the conversations among scientists shifted from curiosity to alarm. Because in physics, repetition implies intention. Natural phenomena decay, degrade, and disperse with time. Artificial ones remain coherent. NASA's Parker Solar Probe caught the edge of the disturbance, recording a small dip in local plasma temperature and a subtle magnetic ripple, aligned precisely with 3I Atlas's trajectory vector. The timing was so exact that researchers described it as clockwork. The second pulse wasn't random radiation, it was structured output, measurable in both electromagnetic and kinetic domains. The data reached the Harvard-Smithsonian Center for Astrophysics 2 days later, where it was subjected to blind analysis. A team with no prior exposure to the case was asked to interpret the waveform without context. Their conclusion: the pulse resembled a modulated carrier wave, something transmitting through the medium of solar plasma itself. When told the source was a cometary object, several thought it was a trick. Still, the pattern held. Every major observatory that observed 3I Atlas that week, from Mauna Kea to La Silla, confirmed faint but consistent periodic spikes in reflected light intensity. The peaks occurred at perfect intervals, unaffected by viewing angle or distance. It was as if 3I Atlas had developed a rhythm that persisted across millions of kilometers. Some tried to explain it naturally. They proposed that the pulse could be caused by rotation, with reflective surfaces periodically facing Earth and then turning away. But rotation produces gradual sinusoidal changes, not discrete pulses with abrupt edges. Others suggested venting or fracturing, but the spectral silence ruled that out too. No gas, no dust, no emission. Just clean, modulated reflection. By early December, the pulse had become the central mystery in every agency tracking the object. The International Astronomical Union issued a terse statement acknowledging periodic reflectivity modulation consistent with photometric interference phenomena. The phrasing was careful, technical camouflage for something extraordinary. Privately, the tone was different. An internal ESA summary described it as the reactivation of a controlled process last observed during perihelion. In other words, 3I Atlas wasn't merely coasting away, it was doing something. Dr. Rafael Gomez, who led the optical monitoring project in Chile, put it in starker terms during a closed briefing. Once is coincidence, twice is command. The room went silent. If 3I Atlas could modulate its environment, then it wasn't just reacting to solar energy, it was using it. The second pulse suggested an active cycle, like a system testing itself after surviving extreme heat. Some even speculated it was a kind of recharging event, the interstellar equivalent of a heartbeat. No one dared publish that theory. But the whispers spread. The pulse faded gradually as the object moved farther from the sun, leaving behind a faint electromagnetic echo in the solar wind, a residue of order within chaos. It was as if 3I Atlas had sent a single, deliberate signal into the void, waited for the universe to listen, and then fell quiet again. For the scientists still watching, that silence felt heavier than any noise, because after the second pulse, the question was no longer what is it doing, it was who, or what, is it doing it for? Any space. Motion demands a cost. Every thrust must burn something. Every acceleration must leave a trace. Heat, vapor, radiation, or debris. Conservation of momentum isn't negotiable. Yet as 3I Atlas drifted away from the sun, it continued to accelerate ever so slightly, gliding through the solar wind without exhaust, without decay, and without explanation. It was first noticed by NASA's Jet Propulsion Laboratory during orbit recalculations in early December. They expected the outbound trajectory to flatten as solar radiation pressure weakened. Instead, the velocity curve held steady. Even at twice the expected distance, the object was still gaining speed, only marginally but enough to register on every precision model. The problem wasn't that the numbers were large, it was that they refused to stop. In theory, this was impossible. No gas jets, no fragmentation, no electromagnetic emissions. And yet the energy budget didn't balance. Somewhere, something was providing sustained acceleration. When physicists ran energy conservation checks, they found a gap, a missing term. It was as though 3i Atlas was drawing power from nothing. The first hypothesis to emerge was solar charging. Perhaps the object's surface was acting as a photovoltaic layer, converting sunlight into stored electrical energy. That might explain the steady glow and the precise, almost mechanical acceleration profile. But if it were storing energy, it should also be releasing it, in radio waves, infrared radiation, or thermal leakage. Every test for such emissions came up empty. The surface seemed to absorb, redirect, or neutralize all energy perfectly. Next came the electrodynamic coupling theory, the idea that 3i Atlas was tapping into the charged particles of the solar wind itself, converting momentum from streaming plasma into propulsion. The equations almost worked, but to sustain thrust for weeks without measurable current would require fields of staggering precision, a level of control unseen in any natural process. The more data scientists gathered, the more paradoxical the object became. It didn't obey the thermodynamics of a comet, nor the inert drift of an asteroid. Its acceleration was too smooth, its orientation too stable. Dr. Amira Torres, the thermal physicist who had analysed its cooling behaviour, summarised it in her notes. It's conserving energy as if it's alive, maintaining equilibrium through intent rather than entropy. At the Harvard-Smithsonian Center for Astrophysics, researchers performed an energy audit across the object's timeline. They traced the cumulative motion since its entry into the solar system and calculated the total energy required to produce the acceleration observed. The result was staggering, comparable to a small fusion detonation, spread out gradually over weeks. And yet there was no fuel, no heat, no trace of conversion. NASA's analysts called this the exhaust problem, not because they couldn't find where the thrust was coming from, but because they couldn't find what it left behind. Every natural engine in the universe leaves fingerprints, photons, ions, momentum transfer. 3i Atlas left nothing but motion itself. One speculative theory suggested that the object might not be using propulsion in the conventional sense at all. Instead of pushing against the solar wind, it might be manipulating space-time curvature, exploiting minute gravitational gradients to create apparent acceleration without expending mass. The concept bordered on the impossible, yet it fit the data better than anything else. As one researcher wrote in the margins of an internal report, if it's not producing thrust, it's producing geometry. By mid-December, the International Astronomical Union released a short technical note acknowledging sustained non-gravitational acceleration inconsistent with observable exhaust phenomena. The statement was cautious, but its subtext was clear. The object was moving without propulsion. In private, even the most conservative scientists began to admit the unspoken possibility. Motion without energy loss meant mastery, a system so efficient that it operated at the edge of physical law. Whether it was natural or manufactured didn't matter anymore. What mattered was that humanity had never seen such precision in motion before. Dr. Eleanor Chandra, whose earlier magnetic simulations hinted at a feedback system, put it bluntly in her closing report. It doesn't move through the solar system. The solar system moves around it. Her words, once metaphorical, began to feel literal. Every measurement of 3i Atlas suggested not an object powered by chaos, but an entity governed by perfect balance, a system where energy wasn't burned, but borrowed and returned seamlessly. And so, as 3i Atlas slipped farther from the sun, it left behind no flame, no smoke, no sign of labour, only the unmistakable mark of power without waste, energy without exhaust, a kind of motion so pure that even space itself seemed to part for it, quietly, obediently, and without resistance. By mid-December, the data no longer felt like data. It felt like a confession a mathematical whisper from something that should not exist, yet did. The readings had all been cross-checked, recalibrated, and re-verified by independent teams across 3 continents. There were no more margins of error to hide behind. Every measurement, the acceleration curve, the brightness consistency, the thermal equilibrium, the pulse rhythm, all pointed toward a single conclusion that no one wanted to speak aloud. It began with a deceptively simple table compiled at NASA's Jet Propulsion Laboratory. One column listed solar flux at each observational point, another showed 3i Atlas's instantaneous velocity. When the two were plotted together, the curve didn't just correlate, it locked in. Every increase in sunlight intensity was followed by a perfectly proportional response in speed, with no measurable delay. It was as if the object didn't absorb light, but understood it, translating photons directly into motion. The coefficient between the 2 variables was exact to the 3rd decimal, a precision that nature almost never grants. That precision sent shockwaves through the modelling teams. Random geological shapes, icy surfaces, or uneven jets cannot maintain uniform relationships like that. Even engineered spacecraft struggle to maintain such stability under solar radiation. For the first time, physicists found themselves facing a curve that behaved more like code than like physics, consistent, deliberate, elegant. At the European Space Agency, data analysts ran a Fourier transform on the recorded brightness curve to search for hidden periodicities. To everyone's astonishment, the frequency peaks weren't random noise. They aligned with harmonic ratios, simple integer multiples of the same base frequency first recorded during the perihelion pulse. That meant the object's luminosity wasn't just varying naturally, it was oscillating in quantized steps, like a pattern written in mathematics itself. Dr. Meilin Zhao, reviewing the results, called it structured physics. Her comment spread quietly through the research networks, half joke, half realization. Because if the ratios were intentional, if they weren't coincidence, then the object was doing more than reacting to sunlight. It was using light as an input. NASA's Parker Solar Probe provided another piece of the puzzle when its magnetometer detected synchronized oscillations in the local solar field. The magnetic ripples lined up with the same frequency found in the optical data. Whatever was happening around 3i Atlas wasn't isolated to light or plasma, it was multi-domain. The object was interacting with the environment in layers, manipulating photons and particles with the same timing. Statisticians were brought in next, not astronomers, but pure data scientists. They were told nothing about the object's identity, only that they were examining a set of correlated signals from space. Their conclusion was startlingly direct. The probability of this correlation being random is less than 1 in 10 trillion. The system displays deterministic feedback behavior. Feedback, a word that belongs to control systems, not comets. The more the numbers were studied, the more they began to sound like behavior rather than consequence. The acceleration profile showed input-output symmetry, as though the object measured solar flux and adjusted its motion to maintain a constant ratio. The reflectivity pattern followed a self-regulating curve. If the light grew too strong, the surface dimmed slightly. When it weakened, the brightness increased. That is the definition of feedback control. To some, this was the moment when 3i Atlas stopped being a mystery of matter and became a question of design. If the object truly responded in real time to external stimuli, then it wasn't passive, it was participating. In one closed NASA roundtable, Dr. Eleanor Chandra asked a question that silenced the room. At what point does a stable system become a decision-making one? No one answered. By now, even the most skeptical analysts were running out of natural explanations. The probability distributions, the harmonic frequencies, the non-gravitational acceleration, each was strange alone, but together they formed a pattern too consistent to ignore. The numbers implied intent, but intent requires a source, and that was the one variable missing from every equation. The official reports avoided the word control. They preferred phrases like self-modulated reflectivity and adaptive photonic response. But among the scientists who spent their nights staring at those immaculate curves, another phrase took hold, one never meant for publication. It's listening to the sun. And that, more than any headline or speculation, was what the numbers truly implied. Not randomness, not chaos, but a quiet, deliberate order humming beneath the laws of physics as if the universe had written a sentence in motion, and waited for us to read it. By the beginning of December, the tone of every report, every press release, and every internal memo had shifted. The language grew tighter, the phrasing turned evasive, because everyone watching 3i Atlas knew what was coming, the point where distance, energy, and silence would converge. December wasn't just another phase in the mission, it was a countdown. The object had now cleared the orbit of Mercury, gliding outward on a trajectory that should have been predictable. But nothing about its motion was following the playbook. Its acceleration remained constant, its brightness too stable, its magnetic footprint still pulsing faintly at regular intervals. By then, the anomaly wasn't about whether something unusual was happening, it was about what would happen next, and when. Every agency tracking the object began planning for the December window, a 10-day period when 3i Atlas would align with Earth's line of sight once more before slipping irreversibly into the outer solar glare. It would be the last opportunity to collect coherent optical data before the object vanished beyond range. Observatories from Hawaii to Chile, from La Palma to South Africa, prepared for a synchronized global observation run. Behind the scenes, the meetings turned philosophical. Some scientists admitted they were less interested in brightness or trajectory now, and more in behavior. Would 3i Atlas pulse again as it did after Perihelion? Would it continue to accelerate? Or would it, as one physicist half joked, switch off? The countdown had taken on the tone of a vigil, waiting not for destruction, but for response. At NASA's Jet Propulsion Laboratory, Dr. Eleanor Chandra gathered her team for what would be the last full simulation before the window opened. The models predicted that, given its current acceleration, the object would exit measurable range by mid-December. But when the team extended the timeline further, something strange appeared. The trajectory bent slightly, not toward any gravitational source, but toward a geometric plane that intersected Earth's orbital path 6 days before the solstice. It wasn't a collision course, but it was close enough to raise eyebrows. No one dared suggest intent, but the word hung unspoken in every discussion. Why that alignment? Why that timing? The data analysts at ESA called it the mirror event. According to their calculations, the geometry meant that for roughly 6 hours on December 14th, sunlight reflected from 3i Atlas would be directed precisely toward Earth, a near-perfect specular alignment. In theory, that alignment should produce nothing more than a brief optical spike. But given the object's previous patterns, the perihelion flash, the second pulse, the perfect light curve, the coincidence felt engineered. NASA prepared contingency, protocols. The Deep Space Network scheduled continuous radar pings, while the Parker Solar Probe was instructed to monitor any plasma variations. Ground observatories were told to record continuously across all wavelengths, visible, infrared, and radio, in case the event carried a signal. Then came the silence before the window, days of quiet observation, data streaming in with nothing unusual to report. And then, on December 13th, just as Earth rotated into position, the brightness curve shifted again, not sharply, but rhythmically. 3 pulses, each separated by the same interval seen at perihelion. Fainter this time, as if repeating a message that had already been spoken once. For 6 hours, the object maintained perfect optical symmetry, the same kind seen in laser calibration mirrors. Instruments across the globe captured the reflection. The light was clean, white, and constant, not flickering, not distorted by the solar wind. Then, at the precise midpoint of the alignment, it dimmed abruptly and stayed that way. To some, it was nothing more than a reflective echo. To others, it was a gesture, a deliberate closing of a cycle that began with the first flash months earlier. In the debriefings that followed, one line from the official NASA transcript summed up the collective unease. No natural object maintains symmetry to this precision, then ends it by choice. After December 14th, the brightness never returned. 3i Atlas continued outward, silent, its trajectory now stable and its acceleration gone. It had done whatever it came to do, and then stopped. Among the scientists who had tracked it from the beginning, the final days were marked by an emotion they could barely name. Not fear, not relief, but awe. The December countdown had not brought catastrophe, but comprehension. A realization that, for a brief window in human time, something had looked back at the sun, responded, and left us to wonder what it meant. and when the last signal faded into background noise, the world's telescopes turned their mirrors away. But the numbers, the pulses, the ratios, the impossible balance remained. Proof that, in December of 2025, for a few silent hours, something beyond comprehension had synchronized itself with both the sun and the planet watching it.